introduction. And yeah, thanks for having me. I'm excited to talk today about mixing and melting at the terminus of glaciers like the one shown here. As Craig said, I'm a professor at Rutgers University, relatively new, and this work is in collaboration with this group here from Oregon State University, University of Alaska, and University of Oregon. And it's been part of a big collaborative project with a whole bunch of different components, but I'm going to focus on my work looking at kind of the ocean processes here right in front of the glacier. And so to start, motivating this work kind of with some big picture, this is a visualization of the Greenland ice sheet with ice velocities shown in color. And you can see these pockets of fast ice velocities where glaciers drain the ice sheet into the ocean. Or more specifically, they often drain the ice sheet into fjords. So this is just one sample fjord in West Greenland. The glacier flows into this long, narrow fjord, and the fjord forms a conduit between the ocean and the glacier. And what I'm going to focus on today are the processes occurring right here in the ocean in front of the glacier, where we have underwater melting of ice and fresh water exported into the ocean. And there are a variety of reasons we care about these ocean-glacier interactions in fjords. So big picture, the Greenland ice sheet and other Antarctica and other glaciers around the world are contributing to sea level rise as they lose mass. So these are observations from GRACE satellite showing ice mass change since 2002 for Antarctica and Greenland. And if you focus on Greenland, you can see it's losing mass at a rate that contributes to about a 1 millimeter per year of sea level rise, which is about a quarter of the total global rate of sea level rise. And if we want to make projections of sea level rise in the future, we need to understand what's driving this mass loss. And one piece in this puzzle is evidence of the ocean playing a role in driving mass loss from glaciers and ice sheets. So if we think about how the ocean can affect glaciers, we've seen this mass loss over the past few decades in Greenland, and it's largely concentrated around the marine margins. It's associated with an acceleration and retreat of many of these marine terminating glaciers. And then it coincided with warming of waters offshore of Greenland. So this map shows just schematically the currents that bring warm waters around the coast of Greenland. And these warm waters of Atlantic origin warmed in the past decade, and that coincided with glacier acceleration and retreat. But we have no direct measurements of the melting that might have actually driven this retreat. So this has led to this hypothesis that warmer ocean waters might be increasing submarine melting and triggering glacier acceleration. But critically, we have no direct observations of melting at most of these glaciers, let alone observations of how that melting is changing over the decades. So that's thinking about how glaciers might affect the ocean. In the other direction, the ocean also has, this should be backwards to the other way, how glaciers affect the ocean. We can think in terms of the increased freshwater from this ice loss. So since the 1990s, sorry, one second, let me just fix this. Since the 1990s, there's been about a 40% increase in the total freshwater that's exported from Greenland into the North Atlantic. And we might expect that this can, have impacts on the ocean circulation at a whole variety of scales, from locally within the fjords, out on the coast, coastal currents and other shelf processes, and then potentially even at larger scale, thinking about deep convection in the North Atlantic and the meridional overturning circulation. So we care about kind of both directions of ocean glacier interactions, how the ocean affects glaciers and how glacial meltwater affects the ocean. And this sort of boils down to understanding exchanges of heat and fresh water. And these exchanges occur in fjords. So this is a typical schematic of a glacial fjord with a glacier flowing in from the right. And I've got it in schematic form up here, and then a satellite image of one example fjord from above. And this is sort of typical of tidewater glacier fjords in Greenland, but also Alaska, West Antarctica, Patagonia, and other places around the globe. And so basically you have a glacier flowing into the fjord, it breaks off icebergs, and then there are two sources of liquid freshwater that are going to be really important for this talk. So there's submarine melting, and that's from the ice melting directly into the ocean. And this is sort of the critical piece by which ocean variability might be driving changes in the glacier. And it's also somewhat of a holy grail of the field that we don't have good measurements of this, but we think it's a critical link. And then the other source of liquid freshwater is subglacial discharge, and that's from surface melt and precipitation that pools at the top of the glacier and drains to the bed and enters the fjord at depth, like a river, but way below the surface. And so we have these inputs of freshwater that are exported into the ocean, and then we have heat that's provided by the ocean to drive this submarine melting. And so understanding ocean glacier interactions involves a whole variety of scales, from the large scale circulation around the coast of Greenland or whatever glacier ice sheet we might be thinking about, down to the boundary layer dynamics that control the exchange of heat and fresh water. And so if we want to think about how the ocean variability might drive changes in the glacier, we need to understand the large scale circulation and variability, say of the North Atlantic current and the coastal currents around Greenland, how that heat is transported through the fjord, and then ultimately how that heat can get across the boundary layer to drive melting. And you can also look at these scales in the opposite direction of what's the fate of all this fresh water from glaciers as it spreads and mixes into the ocean. And so I'm going to focus today on this, the smaller scales of this problem. So what's happening right here near the glacier ocean interface. And so I want to focus on the plumes that drive mixing and melting right near the terminus. And so what we expect is when we have these sources of fresh water, melt and discharge, entering the salty ocean, they should be buoyant and form upwelling plumes. Salinity here is the dominant control on density. And so you expect, buoyant plumes to rise along the terminus. And there's sort of two important things to note: that we expect, within these plumes, there to be a shear-driven boundary layer where the transfer of heat and salt across this inner boundary layer should scale with the velocity outside the boundary layer. And so if you have plumes rising along the glacier face, you expect that the melt rate should scale with the near ice velocity, which might be from a plume, and also with the properties within the plume, the temperature and salinity. And then these plume dynamics are also going to control how this fresh water initially mixes as it enters the ocean. And so importantly, these plumes are sort of a choke point in the system. They control how fast you can get ocean heat and salt across the boundary layer to actually drive melting.
So, sorry, Rebecca, we have a question in the chat from Allegra. Do you mind if I just ask you questions?
Oh yeah, definitely. Go ahead.
Yeah, Allegra, any chance you might want to ask a question yourself, or shall I?
Sure. Can you hear me?
Yeah.
Yep. Sounds good.
Okay. So I've heard from glaciologists that it's not that buoyancy of things around glaciers is not just temperature and salinity, but the sediments that can be ground up, especially if it's things coming off the bottom or that have ground across the land surface, are a significant part of the buoyancy of whatever freshwater melting happens and can make it less buoyant than you think, even if it is freshwater. So are you going to be addressing this?
No, that's a really good question. I'm not going to directly address that. I think in some systems, there's definitely sediment in these plumes. You sometimes even see, there's evidence of sometimes there being so much sediment that you get a bottom gravity current. We do have some measurements from the system I'm going to focus on that show sediment concentrations in the plume right at the glacier, and it's not high enough in this case to affect the density. But I wouldn't rule out that in some systems it might. And I think it's a big unknown. And I've actually been trying to get working on a series of proposals to try to get funding to get use ROVs to try to get measurements of the sediment concentrations right near the grounding line at these types of systems. So the short answer is it's somewhat of an unknown, although the limited evidence we have from the system I'm going to focus on is that by the time it's rising along the terminus, the concentrations are a little too low to have a significant effect on density.
Thanks.
Yeah. Okay, so There's actually two types of plumes that we can sort of characterize along the terminus. The one that gets most of the attention are the energetic plumes that come from subglacial discharge. So you have all this fresh water coming in at the base of the glacier, and it forms a really energetic upwelling plume. It has a lot of buoyancy, and so you expect high velocities along the ice face, and that should correspond to high melt rates. But there's this other regime where you just have buoyancy from the submarine melt itself. It's a much smaller source of buoyancy, and so you expect more weakly upwelling plumes that when they're melting into a stratified ocean, they should form mid-depth intrusions. And because we expect lower velocities in these melt plumes, you might expect that the melt rates associated with this are much lower. So we have these two regimes, and because we expect melt to be much higher behind the discharge plumes, a lot of the focus of previous studies, both observationally and modeling, have been on this discharge plume regime. So in terms of observations that we have near the glacier, they've mostly been focused on discharge plumes kind of as they hit the surface or are flowing away from the glacier. But importantly, we don't really have observations in the upwelling phases of these plumes or close to the glacier where we might be able to characterize what this ambient melt regime really looks like. And just to give you a sense for why we don't have many observations right near the glacier, it's just a relatively small calving event at the glacier I'm going to focus on today. And so it just gives you a sense for why it's really hard to get sort of standard measurements of ocean processes in front of the glacier, and why we need autonomous platforms to probe the ocean and ice boundary. Okay, so in the absence of observations, the field has relied really heavily on sort of a standard theoretical framework for representing melt and mixing. And this goes into all sorts of modeling studies, but also all sorts of studies that kind of just use this framework as a model itself. And the basic idea is that it's using buoyant plume theory coupled to a melt parameterization to estimate melt rates. And so the buoyant plume theory side of things, it's basically four equations for the conservation of mass, momentum, heat, and salt. When you solve them, you can derive the properties of the plume as it rises along the glacier face. So the upwelling velocity of the plume, the temperature and salinity of the plume, the thickness of the plume. And this is a really well-developed theory dating back to the 1950s. It's been tested in a whole variety of other environments, like for volcanic eruptions, discharge of pollutants. It's well tested, and there's, I should say that there's an entrainment parameterization that relates the velocity of the plume to entrainment into the plume based on this empirical coefficient that's pretty well tested in laboratory and other geophysical settings. So this buoyant plume theory side kind of represents the bulk properties of the plume as it rises along the ice face. And then in the ocean ice world, it's often coupled to a melt parameterization. And so the important points of this melt parameterization is that you have the melt on the left-hand side scaling with the velocity. So W is the velocity of this plume rising along the ice face. And that's again, assuming that there's this shear-driven boundary layer, that the transports across this inner boundary layer are controlled by the magnitude of the velocity of the plume out here. And another important point is that there are these empirical coefficients, what we often call heat and salt transfer coefficients, these gammas, and a drag coefficient that shows up here. And so the basic gist of how this is used is that if you know the fjord temperature and salinity, and you know some input of discharge at the base of the glacier, you can use buoyant plume theory to solve for the plume properties as it rises. That will give you the near ice velocity, temperature, and salinity. And then with the melt parameterization, you can relate that to a melt rate. And then the melt rate itself feeds back as a source of buoyancy to the plume as it rises. So it's this nice kind of very simple coupled system. And I'm skipping over the details, but I want you to just have some sense for how this is used. And I also want to point out that this is used to model both types of plumes along the glacier terminus. So again, we have discharge plumes and ambient melt plumes. And with this framework, we expect that the discharge-driven melt should be much larger than the ambient melt, both kind of in terms of local melt rates, but also much larger in terms of the total melt over the terminus. It's the same physics in these plumes, but there are different parts of the parameter space. And then the second thing we find when we apply this theory, and this kind of has become an assumption for a lot of work that builds on this theory, is that melt should scale something like linearly with the temperature of the fjord waters relative to the freezing temperature, and then it should scale with the discharge flux to the 1/3. And in the literature, there's some variability in this 1/3 power, but it's pretty close to 1/3 in most studies. And so what I want to be doing in this talk is kind of looking at these basic assumptions that arise from theory. This framework of plume-melt theory has really proliferated in the literature. It really forms the basis for almost all of our studies of ocean glacier models. But it's pretty much untested with any observations at tidewater glaciers, like these vertical calving fronts. And so just to give you a sense for kind of how this plume-melt theory is used in models, there's a body of studies that just use plume-melt theory on its own, like looking at how melt should vary based on ocean conditions or stratification. There's kind of a first generation of ocean models that tried to resolve the upwelling plumes, but weren't turbulence resolving. And so they basically tried to tune the mixing to match plume theory by adjusting the viscosity and the diffusivity so that the bulk properties of the plume match this expectations from theory. Kind of the second generation of ocean models and some glacier models have decided, that the upwelling plumes are not going to be resolved well within the models, but instead we can just represent them with plume-melt theory and couple that to either an ocean model or a glacier model. So in the ocean modeling case, this would be using plume-melt theory to kind of force the boundary of the ocean model with velocities. Or for a glacier model, this would be forcing, the glacier with melt rates that are derived from this plume-melt theory. And then the fourth variation is that sometimes just the melt parameterization is used alone in models that actually think they're resolving the near ice velocity field. And so then the melt parameterization is just used to relate the near ice velocity, temperature, and salinity to the melt rate without the plume. But that's only feasible for tidewater glaciers if you're modeling at very small scale and actually can resolve the upwelling plumes, or in Antarctica or other ice shelves or ice cavities where you might expect that tides or other modes of circulation that are captured by the model might be the dominant velocity that drives melting. Okay, so I want to kind of prime you about a few things that you might want to be skeptical about in this plume-melt theory. This basically hints at the results I'll be getting to. So if you look on the buoyant plume theory side of things, one important limitation is that you have to assume some geometry of the plume, and that sets the surface area, and that's in turn a critical control on how much net entrainment there is into the plume. And this has been sort of the subject of some previous work of mine and other people's, and I'm not going to get into this today, but particularly for the discharge plume, whether you think of it as a cone plume or a line plume, will have a big impact on what sort of downstream circulation the plume drives in the ocean. But if we look now at the melt side of things, which is going to be a little bit more my focus today, one other limitation here is that this framework assumes that the upwelling velocity of the plume is the only component of the velocity field that can drive boundary layer shear instabilities. So it assumes that this W upwelling velocity is the only source of energy to drive transport across the boundary layer. But other modes of circulation could be important for enhancing transfer across the boundary layer. And then last, this is based on using these empirical coefficients that are entirely untested at tidewater glaciers. The transfer coefficients here have been derived from studies of sea ice and ice shelves, which are relatively horizontal ocean ice boundaries where buoyancy is stabilizing. But in this setting, we're looking at relatively vertical ocean ice boundaries where you might expect really different values for these coefficients. And then again, these drag coefficients are also untested and assume a relatively smooth ice face. So there's these things we should be skeptical about in the basic framework for plumes and melting. And there's also a growing body of work suggesting that we might be underestimating melt. And these are sort of indirect studies pointing out that the total melt along the terminus seems like it should be higher than what we estimate with theory. And this is one example on the right here, which is a modeling study by Donald Slater, where he shows that ambient melt rates should be enhanced by horizontal velocities, that the discharge plume can set up recirculations that drive velocities over more of the terminus. So what I want to do for the rest of this talk is show some near glacier observations that we've collected and try to address sort of two parts. The first that kind of spans the whole talk is trying to really quantify the melt rates and the discharge fluxes. These are important quantities for ocean glacier interactions, but they're actually very poorly constrained with observations. So what are the melt rates? And then I want to try to compare the observations with what we expect from theory, and particularly these two sort of assumptions that come out of our theory. The first is that we assume discharge driven melt is much larger than ambient melt. And in the first part of the observations, I want to be really looking into this and show some observations of the ambient melt regime. And then in the second part of what I'm going to show, I want to look more at like the bulk picture of as we try to work towards an accurate representation of or parameterization of melting as it relates to ocean conditions and discharge. I want to test this sort of common parameterization that arises from the assumption that discharge is really the dominant driver of melt. So these kind of 2 points that I'll try to test largely map onto kind of the first and second part of what I'm going to show. Okay, so we're going to focus on LeConte Glacier, which is in Southeast Alaska. It's somewhat similar to the tidewater glaciers in Greenland and elsewhere, although it is smaller scale. It's about 1 kilometer wide and 200 meters deep. It's much more accessible than a lot of glaciers in Greenland, and so it's kind of a nice geophysical laboratory to do really intensive surveying right near the ocean ice boundary. And it's also a nice setting because in some sense the forcing conditions are really cranked up. For some parts of the year, the ocean temperatures are very warm, about 8 degrees, and for some parts of the year, there's a really large flux of subglacial discharge. And so this glacier kind of experiences a really wide range of conditions, which is nice for exploring how melt varies with these forcing conditions. And the glacier is flowing in here at about 20 meters per day, which is similar in speed to a lot of Greenland, the bigger glaciers in Greenland. And as I mentioned before, this is part of a large ocean glacier field campaign over 3 years. I'll be focusing mostly on some of the ocean data we've collected from both autonomous kayaks and ships. There's also some numerical modeling of the fjord being done by Alex Hager. Right at the terminus, we have submarine measurements of the terminus from multi-beam sonar and subaerial measurements from radar and time-lapse camera. And then up on the glacier, we have a whole variety of measurements, but the ones I'll mention briefly are weather stations and surface mass balance stations, which feed into a surface mass balance model of basically how much melt and precipitation is draining in the glacier catchment basin. And this is, a big collaborative project with this group listed at the bottom. And so what I'll focus on next is surveying done by autonomous kayaks. So these are basically kayaks equipped with a jet engine and a remote control. And they're developed by Jonathan Nash and his group, the Ocean Robotics Group at Oregon State. And we put an ADCP to measure ocean velocity and a CTD to measure water properties from the surface down to the bottom. And we send them up to the glacier while we stay back in the ship at a safe distance. And so you can see here the kayak surveying in front of the glacier. This is the kayak here for scale. That's a seal right there. Hopefully this is coming through in good enough quality. And you can see the plume boiling up to the surface here. So we send the kayaks in to get these measurements. And we had some close calls, but luckily we've never lost any kayaks or instruments so far, knock on wood. But this also just helps illustrate why we stay back in the boat and send these relatively disposable kayaks up to the glacier. So this allows us to do a ton of near glacier surveying, I'm going to focus on an intensive campaign in September of 2018, where the kayak surveying in green, we got a whole bunch of repeat velocity sections and 145, casts of water properties. And then this is complemented by a bunch of ship surveying, kind of more standard approach where we make transects with the ship. And in the second part of these results, I'll show some of the surveys over 6 different field campaigns across a wide range of conditions.
We have another question from Allegra in the chat. She's asking how long are the kayaks, and she says the kayaks are really cool.
Yeah, they're about the size of a normal kayak you might use. So I want to say like 12 feet maybe. Is there anything for scale here? Yeah, there's a little, like, yeah, maybe 2 people long if you're head to toe.
Yeah, that looks like really, really good fun. Do you just control them from the boat with a little remote control?
Yeah, they have a couple different settings. If you're somewhat close to them, you can actually just use a remote control. And we actually, for most of the campaigns, we brought some undergrads up to do the field work, and some of them were really into video games and were terrific at driving the boats around with remote controls. When we're a little further back, or if we're doing a long deployment, you can also program it with waypoints on a computer and use either satellite or radio communications.
Thank you.
Yeah. Okay, so what I want to show first is looking at sort of the regimes of melting along the terminus. And so when we survey near the glacier, the most dominant thing we see in the velocity field is the discharge plume. And this is what we expect. There's a ton of fresh water coming at the base of the glacier. It drives an energetic circulation. And when you look at, this is just an example of a cross fjord section of velocity, there's this strong outflowing plume core in blue with a return flow in red, and associated temperature and turbulent dissipation. And so, we did a ton of surveying of the discharge plume, and there's a lot of neat stuff in that data. But overall, kind of the basic signal is what we expected, and based on previous observations and modeling. But what wasn't what we expected is the water properties we saw when we got really close to the glacier, right up near the terminus. And so to give you a sense of kind of what we would expect, as I mentioned, ambient melt looks like it'd be negligible according to sort of standard plume melt theory, where if you modeled the melting over the terminus for LeConte, this is the submarine terminus of the glacier, and just modeled melt rates where you might expect really high melt rates of about 10 meters per day behind the discharge plume, and then really weak ambient melt rates of about 0.1 meters per day. And if we look a little more into what's behind this expectation, so ambient, if you apply this plume melt theory to the ambient melt regime for LeConte, this is depth versus density. So this is kind of the ambient fjord stratification. And what you expect from theory are really low upwelling velocities here and really low associated melt rates. And each of these little cells is an ambient melt plume that upwells weakly and then intrudes when it reaches its neutral buoyancy. And so these are predictions for what you expect kind of in the upwelling plume based on theory, or upwelling plumes, these stacked plumes. And then you can also look at theory to ask, what would the intrusion look like as it exits into the fjord? And so for that, I'm going to plot now depth versus temperature and temperature versus salinity. And again, these gray dots or gray lines are profiles made about 1 kilometer from the glacier. So kind of the downstream away from the glacier profiles. And if you put the predictions from theory on here for what ambient melt intrusions would look like, they're these little blips with about a 0.1 degree temperature anomaly and 0.1% meltwater content. And so until this project, we haven't really had any thorough characterization of these ambient melt intrusions. But that also wasn't too surprising, because if there's such a weak signal, they'd be hard to see, and you'd expect something like this to be sort of smeared out by the time you make measurements downstream. But the observations we actually got near the glacier looked quite different. So this is just a set of sample casts in red right near the glacier. And you can see these big temperature anomalies of often over a degree, these cold layers that are associated with big excursions in temperature and salinity space. And to interpret this, we can add mixing lines. So, how would we expect fjord waters to be modified if they mix with these two types of glacier freshwater? So the blue lines are from mixing with submarine meltwater. So that's if the fjord waters mix directly with submarine melting. And then the green lines are if fjord waters mix with subglacial discharge. And you can see at the surface, there's this pool of discharge modified waters, and that's kind of what we expect. We have this discharge plume flowing away from the glacier. But these cold layers fall right along the submarine melt mixing lines. And so they look like a product of ambient melting, of the ice face melting directly into the ambient fjord waters. And they're a much bigger signal than we would expect. And so for each of these intrusions that we observe, we can kind of define a bunch of properties. I'm not going to get into the details, but we can quantify things like the meltwater content and the temperature anomaly of the intrusion, and how far, a scale for how far the plume or intrusion has risen before, a scale for how far the plume has risen before it intrudes into the fjord. And if we look at the distribution of these intrusions, I'm plotting here bin average quantities as a function of depth versus distance from the glacier, where the glacier is here on the right. And this first panel is sort of the mean temperature anomaly. And it's basically averaging over a lot of these intrusions. And you can see there's this cold temperature anomaly relative to downstream, right near the glacier. But there's effectively no signal of these intrusions once you get out to about 400 meters. And I think we can explain that by looking at the kind of mean velocity field, which now is shown here, where the layer where these intrusions are found is, for the most part, flowing towards the glacier at depth. And then we have the outflowing layer near the surface. So this is that exchange flow set up by the discharge plume. We can see it also if we look now in a cross fjord section. So this is looking across the fjord, where this blue region is the outflowing discharge plume, and the rest of the flow is primarily being sucked towards the glacier and trained into the discharge plume. And so we get this picture that these intrusions are forming along the ice face, but they're actually kind of fighting against the larger scale circulation. And so we don't ever see them more than a few hundred meters from the glacier terminus. And we can sort of see this also by looking at a composite of the intrusions at the scale of the intrusions. So this is basically showing the average characteristics of intrusions by making a composite with 95 intrusions that we observe. We see that they typically have a cold temperature anomaly of about -1 degree relative to the downstream profiles, and meltwater content of about 1%. They're associated with a peak in stratification, and they're flowing away from the glacier at about 3 or 4 centimeters per second relative to the larger scale velocity field. And then we also can define other average quantities like the average thickness, about 17 meters, and the average vertical rise of these plumes is about 30 meters. So these are somewhat robust quantification of things we can measure. Can take it a step further with a sort of hand-wavy scaling for the melt rate based on conservation of melt in 2 dimensions. And so if you think that the meltwater exported in intrusion coming out here should be roughly equal to the melt along the vertical rise of the plume, we can write this simple expression with the average melt rate times the rise of the plume is equal to the melt exported in the intrusion. And if we evaluate this with the 95 intrusions that we observe, we get that we estimate the melt rate, the average melt rate, to be about 6 meters per day with relatively large bootstrap confidence intervals. And so this should only be considered a scaling, sort of an order of magnitude estimate. But I want to put it here just to kind of give you a ballpark of what these intrusions alone suggest about the melt rate. But what we can do is kind of a more rigorous comparison of the intrusions with predictions from theory. And so if we compare what we see with these observations with sort of the standard way that theory is applied, we see that the melt content in the intrusions is about an order of magnitude higher than theory predicts, as is the vertical rise of the plume. So the scale of these intrusions is much stronger and bigger than we might expect. And perhaps the melt rate is about 2 orders of magnitude bigger, although I've put this in gray to highlight its uncertainty. And so what I want to do now is think about like what adjustments could we make to theory that might help explain this discrepancy. And so I want to go back briefly to this slide where I talked about some of the things we should be skeptical about. And one is that these coefficients are untested in these environments. There's kind of no reason to trust that they're the right values when they've been derived at horizontal ocean ice interfaces. And then second is that we're assuming that the only velocity that can drive melt is this upwelling velocity. But what I want to try to do here is, play with the coefficient values, but also play with adding, other components of the velocity, like a horizontal velocity field that could enhance turbulent transfer across the boundary. So if I just click back and forth here for a second, this is basically adding, a second horizontal component to the velocity field along the ice that could be enhancing melt rates, and that the plumes themselves aren't the only thing that can enhance turbulent transfer across the boundary layer. And this is motivated by observations, previous studies, like I mentioned, Donald Slater's work, and also work done in this system where we know that a discharge plume, similar to what Donald showed, the discharge plume sets up energetic recirculations. These are some velocities derived from iceberg tracking, or we can actually try to sort of quantify the along ice velocity with the kayak data, which is shown here on the right. And the basic gist here is that if we use the kayak to try to quantify, away from the discharge plume, what's the rough magnitude of along ice horizontal velocities, we find that this, the mean horizontal along ice velocity is about 0.2 meters per second. And then that's relatively large compared to what we expect for the weak upwelling of these plumes. So this looks like an important component of getting these melt rates right. So if I go back to this, this table, I can add, a few different variations. And the first one here is adding, a kind of unrealistic horizontal velocity field, but saying how much velocity would I need to add to match the properties of the intrusions in terms of the melt content and the vertical rise. And so that requires about 0.9 meters per second of horizontal velocity. And when you do that, the plumes have a much larger vertical upwelling velocity and much larger melt rate because enhanced melting is driving enhanced upwelling. I can also play around with, if I just adjusted either the drag coefficient or the turbulent transfer coefficient, again, to match the observed properties of the intrusions, find that the drag would have to be increased by about 2 orders of magnitude, or the turbulent transfer by about one order of magnitude. But again, they're untested. And then, maybe the most realistic is using what we know to be roughly the magnitude of this horizontal velocity field and, filling in the rest with some adjustment to the coefficients. And, the important thing is I can't pinpoint the right answer with just this data. Adding the realistic velocity gets you about halfway there, but you probably need more than that. And there's no reason to think that there's not multiple problems with this theory. But the important point is that with kind of any of these variations, when you adjust theory to match the properties of the intrusions, you end up with melt rates that are about 3 to 6 meters per day. And that's about 100 times what you'd expect from sort of standard theory, the way that it's applied with standard coefficients.
Rebecca, can I interrupt you? So we have another question in the chat. It's from Vivian.
Yeah.
Vivian, would you like to ask a question? I can ask. So how representative are observations from this glacier from upwelling plumes at tidewater glaciers in general? How representative are observations from this glacier for upwelling? So she's asking you, I suppose, how well do you think your observations of this glacier are a good representation of all glaciers?
Yeah, and I think I'll get into that a little bit more in the next part, where I try to compare, like when I look across a range of conditions and I try to put that in the parameter space with Greenland fjords. I think that in some conditions, the kind of forcings are ramped up, but the basic physics should be very similar, like kind of the fundamentals of how these plumes arise along the ice face. This is on the smaller end of glaciers, but there are glaciers around the globe in Greenland that are, so I'd say that, I'd say mostly stay tuned for this next part, and hopefully that'll help answer a little bit. But I definitely hope and think that what we're doing here should, provide some insight into some of the fundamental processes that should be applicable more broadly.
I think bringing in the along ice shelf flow is really interesting. Do you have an idea of the potential for the local winds driving this relative to the, I think you mentioned that it's driven more by the meltwater plume dynamics?
Yeah, it depends on the system, but for these glaciers entering fjords, so I'm really focused on glaciers that flow into like long narrow fjords, and I've done some previous work on wind forcing in fjords, and I think it's really important for looking at the fjord scale, transport of heat and fresh water. But most of our models and theory suggest that the velocities driven by wind forcing in fjords should become quite small near the head of the fjord, and so it's a little hard to expect that you get velocities this big to be a significant modifier of the kind of melt velocities that drive melt. But it's a good question, and I think in some fjords that have really strong wind forcing, the winds are really important, especially as you get to slightly larger scales of how heat and fresh water are transported through the fjord.
Thanks.
Okay, so, and then, okay, the last line here that I basically what I'm going to show in the last part of this talk, that we have independent estimates of the total fluxes coming off the glacier, and I'll get into this, but they also suggest, a melt rate across the terminus of about 5 meters per day. So kind of just another somewhat corroborating piece of evidence. And then the final piece I want to mention that aligns with this idea that melt rates are significantly higher than we expect from theory. It comes from a recent paper of ours. This is led by Dave Sutherland, where he's used multi-beam sonar of the submarine terminus and radar of ice velocities and iceberg calving to quantify melting. Arguably this is the most direct measurements of melting we have at any tidewater glaciers. And so what he's done is look at the change in terminus position between pairs of scans from the multi-beam, and then he removes the ice velocity, and then discards locations where there's iceberg calving, and that gives a relatively direct estimate of the submarine melt rates. And when he does this in this survey in August, finds about an average melt rate of 5 meters per day across the terminus. And this is from a different year, but it's in same system, but different year and similar, late summer time period. So it's not directly comparable to the surveying that I just showed, but it's, it's similar ballpark of 5 meters per day across the terminus, suggesting that these ambient melt rates really are much higher than we would expect from standard theory. So to summarize this part about ambient melt, I've shown that the total melt across the terminus seems to be about 10 times higher than predicted because ambient melt is about 100 times higher. And this comes across in the kayak surveying of the ambient melt intrusions, and also melt estimates from multi-beam sonar and kind of bulk fluxes that I'll get into in the last few minutes of this talk. And then, these kayak surveying allows us to make sort of a novel characterization of the ambient melt regime at tidewater glaciers. And we find that it's an important part of the total melt, but it's not visible downstream. So you need kind of new observing platforms like kayaks or other autonomous platforms to observe this signal. And it seems that the ambient melt intrusions are ubiquitous right along the terminus, but get entrained into the discharge plume, and so you don't see evidence of them downstream. And then, through exploring modifications to theory, it looks like adding the horizontal velocity field that can be spun up by the discharge plume seems like an important piece, although doesn't go all the way in closing the gap between theory and observations. And another likely culprit is, these untested coefficients for turbulent transfer that are used in the theory. Okay, so I want to spend the last bit of this talk looking across a wider range of conditions. What are the melt rates and discharge fluxes, and how does the total melt vary as a function of fjord conditions and subglacial discharge? So, I just showed results from a really intensive survey, but across a wider range of conditions, how does this basic kind of bulk parameterization that I mentioned in the introduction, how well does this work? And you might recall this is based on this assumption that discharge-driven melt is dominant. And I just showed that, ambient melting actually seems to be pretty important. So, how does that then reflect what we might expect for the total melting along the terminus? And, ultimately we want to be able to have a good bulk parameterization like this to use in ocean glacier models. Okay, so what I'm gonna do here is talk about, estimating the bulk fluxes of these two sources of fresh water from like a slightly zoomed out view, like this goat overlooking our glacier who was caught on our time-lapse camera. Okay, so the gist of this is that we can infer freshwater fluxes from ocean budgets. This is sometimes called Fluxgate method. And it's a method that was first developed by Rowan Moedica in a few papers, and then further developed in this paper from 2016. And the basic idea is that if you have velocity, temperature, and salinity measurements at some fjord cross section, you can evaluate temperature, salt, heat, and mass budgets for the waters upstream of that section and use that to back out the freshwater fluxes. And so, a salt budget for this control volume is used to infer the total freshwater flux. And then by combining the heat and salt budgets, you can partition that into submarine melt and subglacial discharge. And I should note that these have different signatures in the budgets because submarine melt requires latent heat from the ocean to melt, whereas discharge comes in already in liquid form. So if you combine the heat and salt, you can actually separate the fresh water into these two pieces, which again are usually really unconstrained at glaciers, the magnitude and variability. So basically I evaluate these budgets with 82 repeat sections of velocity, temperature, and salinity over 6 different field seasons. These are just 2 sample sections of velocity, salinity, temperature. You can see blue, that's the outflowing discharge plume with this compensating inflow in red towards the glacier. And we have all these repeat sections from about 1.5 kilometers from the glacier here. And so I basically take pairs of transects and I calculate these total melt and discharge fluxes. And then you'll see error bars on these estimates that try to reflect the incomplete spatial coverage and temporal variability. And so basically what I'm doing with these budgets is sort of 2 things. The first is like testing how well does this method work. And one thing we can do is compare the budgets with results from other estimates. One estimate that I'll compare it with, so we have these ocean budgets from measurements in the fjord, and I'll compare it with the surface mass balance model that predicts subglacial discharge based on upstream measurements. And then kind of getting at the crux of it is, how does submarine melt vary with the discharge flux and other fjord conditions? And I'll look at this across, a bunch of different seasons. Okay, so this is, in the background here is a surface mass balance model run by Christian Kienholz, which, predicts, high discharge in summer, going to 0, close to 0 in winter. So again, this is what we expect to feed the subglacial discharge into the fjord. And then the colored stripes are where we have these oceanographic surveys that I'll be focused on. And so you can see they span a range of conditions from very low discharge in early spring to high summer melt conditions. So we're looking across a wide range of discharge conditions, but also a wide range of fjord conditions. So this is depth versus temperature and depth versus density for the 6 different field campaigns. You can see, a wide range in temperature and stratification conditions. And we can make a parameter space here of the average stratification versus the average temperature in the fjord, with each dot being the conditions in each of the surveys. And then I've put, 4 of the largest Greenland fjords on here in diamonds. And so you can see we're spanning part of the parameter space that's quite similar to, fjord conditions in Greenland, but we also have some conditions in summer where the temperature and stratification are much higher. Okay, and the first thing we can do is compare subglacial discharge from the model with our budgets estimate. So I've added here the ocean budget estimates in red dots. And you can see they match up fairly well, except when they don't quite as well. But we can look at this a little more in detail by plotting, for these time periods where we have both estimates. We have the surface mass balance model versus the ocean budgets. And you can see that the best fit in the dashed line here is really pretty close to the one-to-one line with an R-squared value of about 0.79. So this does pretty well, or at least definitely better than I expected. It's not entirely clear which axis here you should consider kind of the more reliable estimate. Basically, neither method, the surface mass balance models or ocean budgets or flux gates, have been really tested at marine terminating glaciers. So this is novel in some sense that we actually can compare upstream and downstream observations of these freshwater fluxes and see how they compare. And overall, it's promising, I guess, promising for both approaches. Okay, and then we can get maybe at the heart of this, which is looking at how submarine melt might vary as a function of subglacial discharge. So again, each point here is from these pairs of surveys where I evaluate the budgets and I can get a total meltwater flux and a total discharge flux. And each of the colors corresponds to a different field campaign. And you can see the melt fluxes vary from about 4 to 20 meters cubed per second, while the discharge flux varies from about 2 to 400 meters cubed per second. So there's a much larger range and magnitude in some of the discharge fluxes. And one basic thing you can notice is that melt does seem to vary as a function of discharge. And as a first step, we can compare these fluxes with what we might expect from the standard plume-melt theory, where each of these lines is a prediction for each of the seasons based on sort of the standard formulation. And as you might expect, based on everything I've just said, these predictions are much lower than the melt we observe by about an order of magnitude. So the bulk melting, again, is about an order of magnitude higher than we'd expect from theory. But interestingly, they both show this dependence on discharge. And with these budget estimates, we're actually able to look at melt across a much wider range of conditions than what I showed in the kayak surveys. Okay, so we can convert these melt rates into a terminus average melt rate by taking into account the surface area of the glacier. And we get melt rates of about 4 to 12 meters per day. And this allows us to compare directly on the same plot with some of the estimates I talked about previously. The estimate of melt from the kayaks falls here in yellow, and then the multi-beam sonar and these two other rectangles. And you can see they overlap pretty well, or if we're thinking in orders of magnitude, they agree pretty well. The multi-beam sonar is a bit lower than the flux estimates, but we might expect the multi-beam sonar to be biased low because Dave has to throw out the locations along the terminus where icebergs have calved off, and you might expect the highest melting to occur where you have calving, since those two things are likely related. Okay, I'm running a little late, so I'll try to wrap this up quickly. But basically, if we want to look at what is the relationship between melt and discharge in the observations, I'm now just plotting this in a log-log plot. And basically, from theory, you expect a slope of about 1/3, and the best fit to these observations is about 0.38. So remarkably similar to what we expect from theory. And this is exciting because we actually have the observations here to really test this relationship that's used so widely in the field. I'm going to skip this and just end with this slide here where, as I've shown before, the observations are significantly higher than we expect from standard theory. But what I want to add here are some of those adjustments that were proposed based on the kayak surveying. So the dashed line here is, if you adjusted the coefficients in the melt parameterization to match the kayak observations, and you only adjusted the coefficients, you end up with a relatively weak dependence on discharge. But if you go with the scenario where it's both an adjustment to the coefficients and you include the horizontal velocity, you can get a curve that actually roughly tracks what we see in the observations. And And to do this, I'm using the horizontal velocity we observe from that September intensive campaign. And then I'm assuming that the horizontal velocity field scales with the energy of the discharge plume. So that's, that's a pretty big assumption, but it's plausible that we might expect the more energetic the discharge plume, the more energetic the kind of larger field across the terminus is in enhancing melt. And so, this is sort of interesting that this totally separate analysis from the kayak surveying that was done before this analysis of the total freshwater fluxes does provide at least one plausible scenario where you might end up with a scaling that can capture the basic trends we see in the observations and with the right magnitude of melting. Okay, so I'll just conclude here by saying, we've been able to, in the second part, sort of test how well we can constrain these freshwater fluxes through the fjord, and we find a relatively good agreement between what we see coming through the fjord and predictions from upstream on the glacier. And then when we look at kind of the relationship between melt and discharge, we find that the observations actually do follow the theoretical scaling of melt scaling with the discharge to the 1/3, although the magnitude is much higher. And the scaling comes from the assumption that discharge is the dominant driver of melting. And so it might be that, even though ambient melt is very important, and it's not directly driven by the discharge plume in the way we standardly think about it, it might still scale with the discharge plume through sort of secondary velocity fields that enhance melting. And so ultimately, we want to work towards, a bulk parameterization that's physics-based and tested with observations in order to better represent ocean-glacier interactions in models and work towards understanding how ocean variability can drive glacier retreat or how glacier meltwater can drive ocean circulation. And hopefully this work is sort of a step in that direction. And I'll end there. And happy to take questions.
Thank you very much. That was fascinating talk. I should get some sort of canned applause or something. So if anybody has any questions, please raise your hand or mention them in the chat. There's a couple of questions in the chat going on from Allegra. So I'm just going to encourage her to speak up at this time.
Can you guys hear me?
Yeah, thank you.
So I had a couple of questions. One, so when you are estimating the surface mass balance of the glacier itself, whose surface mass balance or how are you coming by that estimate? And my other question was about, besides temperature and salinity, do you think about using things like water isotopes to do more constraints on like how much mass is being exchanged?
Yeah, okay, so the first part, the surface mass balance model is run by Christian Kienholz at University of Alaska and Jason Amundsen. And they basically have, they've put a bunch of, we have weather stations and surface mass balance stakes, I believe, on the glacier. And then Christian has used those sort of to calibrate his surface mass balance model. So I don't know the details of how he's doing it, but it's in one of his published papers, and I think fairly standard approach, but using or calibrated with observations from the glacier during the surveying period. And then the second question about I think isotopes and other things we can measure in the ocean. In this case, we haven't made any other observations like that at LeConte, but they are very valuable. I mean, actually, noble gases are a really valuable tool for measuring the meltwater content in the ocean. And that's been used around Greenland and Antarctica to trace meltwater. And even in very small concentrations, you can see a really nice signal of noble gases when they're measured around the coast of Greenland. So that's a great tool. I think isotopes can work, although it's a little tricky separating sea ice and glacier ice sometimes. I forget the details of it, but there's definitely work also, using various isotopes.
Thanks. Appreciate it. This is a great talk. Thank you.
Thanks.
Next, I think I believe David had a question.
Hi, can you hear me?
Yep.
Hello? Hi,
Hello?
I'm on the edge of the internet. Literally. Hi. Any sound?
You're breaking up a little bit. The question is in the chat if we have issues.
I can just try to speculate on based on the question
Hi,
in the chat.
Rebecca. Lovely talk.
You're breaking up, I'm afraid, David. But we can see the question in the chat. The question is velocity question mark, roughness question mark. I suppose
Well, I'll take the second part of that question. I'm not sure what the velocity part is, but roughness is definitely a really good question. And I think it's not well quantified for these tidewater glaciers, but it should be an important control on how fast the ice is melting. And so actually we you know, hopefully I'll have a better answer to some of that in a few years, because we just got funding to go back to LeConte and get you know, boundary layer measurements. So what I just showed was kind of like a step forward in getting the first 100, 200 meters well measured. And what we're hoping to do next is get boundary layer measurements at the scale of meters to centimeters, and including really characterizing the small scale morphology of the ice that might be important for drag. So that's something related to maybe what, but I'm not sure. It looks like Olga maybe has a few questions.
Yeah, great talk, Rebecca, and it's great to see such data. So yeah, my 3 questions. I didn't get exactly whether you treated your gammas, those gamma transfer coefficients, as constants, or was it a function?
So I've treated them as constants. I mean, it's in the literature, it's a little confusing that, you know, sometimes the, depending on how you talk about it, sometimes the transfer coefficient is a function of the velocity field, but I'm
Like other things, yeah.
Yeah. So I'm keeping the velocity dependence, you know, outside of the constant, but I'm just exploring
because
constant values.
Yeah, I'm sure you probably have seen a paper from Patrick Himberg and Veronica, I'm blanking on her last name. So they do show a strong dependence whether it's constant or it's a function. The other one, you haven't mentioned the entrainment rate at all. I mean, I know from my own experience with melt channels, I did the same. I use the same plume model, and if you ever slightly even change it, everything like goes haywire in either direction. You have so much more melting, and the entrainment rates, again, they are parameterized. I wouldn't bet that parameterizations from sea ice and from, say, subice shelf melting of any use at all. But yeah, what about the entrainment rate?
Yeah, that's a really good question. So some of my previous work that I didn't talk about at all has looked more at the sensitivity of the, you know, entrainment and the surface area. You know, like I think I mentioned a little bit in the talk that you assume some entrainment coefficient that relates the plume velocity to the entrainment into the plume, and you also assume some surface area, and the net entrainment is going to be really sensitive to that surface area. And so, you know, I have some previous work, you know, exploring observations from Greenland and how that, you know, bulk entrainment, yeah, how things are sensitive to that. You know, what I've found here is that for the ambient melt intrusions, when I play with a range of entrainment coefficients, the net melting actually isn't that sensitive in this particular regime. But when you're looking at the discharge plume and the kind of if you're looking at what happens downstream, it's really sensitive to that.
And let's get to the discharge, not of the plume, but the discharge. If I understand correctly, you assume that everything goes through the subglacial discharge. So there is like a channel or something, and not outflow at the base of the glacier. But if you look at your surface, or rather how it looks like, there are a lot of crevasses and everything. So my question is, what about the end glacial discharge? So those things that you showed at some depths above the bed, water could just seep out from there. Do you have a sense, or do you have a way to distinguish and separate and say, no, there is no glacial discharge whatsoever, and everything is truly driven by the subglacial discharge?
Yeah, so yeah, we generally do assume that most of the discharge comes out at the bed of the glacier. I don't think actually any of the results I presented here hinge on any assumption about where the discharge is coming out. It's a tough, because
no, because then that's, you need to be in buoyancy where it goes out. So because to get like 30 meters, you need to entrain and melt a lot. And if say you discharge at the level of like 23 meters above, so it's much less of like work against gravity to go a little bit up and horizontally.
Yeah, definitely. If you were looking at the properties of the discharge plume and saying, how does that relate to what's happening in the upwelling phase, it would be really important to know what depth it's coming out at. But actually in the, when I characterize the ambient melt, where there in those intrusions I was showing, there actually is pretty clearly no modification from discharge. So that those, like there isn't discharge being mixed into those ambient melt plumes. Those are occurring away from the discharge plume and have properties that are consistent with just fjord waters mixing with submarine melt sort of directly. But I think, from other observations I didn't show at this system, we do see a pretty clear signal of like an energetic discharge plume that comes out where you would expect the discharge to be routed based on, the bed of the glacier at the deepest point.
Well,
but it's true, we can't rule out that there might be some in-glacial.
And the same goes with whatever computations of freshwater runoff, what you're calling SMB, it's not exactly mass balance, but anyway, because you can have a storage in glacially, so in whatever is computed based on temperature, part of it can be stored in glacially and then discharged at some other time. So there might be some lag in that.
Yeah, and actually I should say that the best correlation between the downstream fjord measurements and the upstream SMB model is 1 day lag. And so, yeah, definitely there should be storage, and we've looked at kind of, a lagged correlation across a bunch of lags, and it does seem like there should be transit time, and there could be some storage for sure.
Great, thank you.
Yeah.
Great.
Hi, it's Allegra again. I don't know if this was Dave's question exactly, but about the roughness. So surface roughness length is something that most SMB models are pretty sensitive to. So I'm curious if that's what Dave meant and he was asking about, if it was something having to do with the sea ice or the icebergs.
I would guess that he was asking about the roughness of the submarine face of the glacier. Because yeah, when I talk about roughness, I wasn't talking about on the surface of the glacier. And I wouldn't have much to say about the SMB model and what you might expect in terms of surface melt, but in terms of the submarine melt of the ice face, it should be a function of the roughness that we actually haven't really characterized at any tidewater glaciers at the small scale. I think we're starting to have all these observations of the morphology of the terminus at the scale of tens of meters to hundreds of meters, from like Dave Sutherland's work, and other groups have done multi-beam sonar imaging, but we're lacking kind of the small scale that would give us an appropriate drag coefficient that then goes into the melt parameterization.
Thanks.
Cool. Thanks, Greg, and I'll be on. Yeah.
There's a moment I can speak. Yeah, no, I've got to head off, everyone. But thanks so much, Rebecca, for speaking. And
yeah, thanks a lot for having me.
So I'm going to leave this running in the background if anybody wants to ask any further questions.
Okay, thanks a lot.
See you guys for now.
Cool. Well, I'll sign off unless there's any more questions.
Oh, it looks like there's been sort of a mass exodus.
Yeah. Well, it's 12:15. That's understandable. All right. Thanks a lot. I'll see you guys later.
Yeah. Thank you.
Bye-bye.